Okay, hello everyone. I'm Mingdai. Today I'm very glad to share our paper instruction-based hypergraph pretraining with you. And before we talk about the hypergraph pretraining, I would like to introduce some backgrounds on graph pretraining. One benefit of graph pretraining is knowledge transfer. By pretraining, we can preserve the knowledge from large and diverse graph data sets for specific downstream tasks. And we can further fine-tune on the pre-trained model for better performance and efficiency. The other advantage is the ability to learn robust representations. Training helps in developing generalized representations of graph structures and node features. Despite these advantages, graph pretraining has its own challenges. Some previous works adopted self-supervised learning to address the lack of labeled data in the pretraining stage. But there usually exists a gap between the self-supervised training objectives and the downstream training objectives, leading to a suboptimal performance in downstream tasks. Even if labeled data is available during the pretraining stage, the graph used for pretraining may differ from those graphs in the target tasks. For example, some nodes are missing and some nodes are added in the downstream tasks. This can also affect the effectiveness of the pre-trained graph models. In this paper, we apply prompts to solve those challenges in graph pre-training. Prompt learning has shown great success in pre-training the large language models. However, since the format of plain text does not naturally align with the graph structure data, it's not straightforward to apply prompts in graph. One simple idea is to prompt information to a certain part of graph through edges. In this way, the prompts can participate in information propagation during the graph learning. However, dyadic edges in traditional graphs can only propagate information through simple pairwise relationships, which is neither flexible nor efficient. Therefore, we believe that the hypergraph where each hyperedge is able to connect multiple nodes simultaneously is a better structure for prompt-based pre-training in graph tasks. About design of the prompt, although there are already some previous works on prompt-based graph pre-training, most of them use soft learnable prompts for different tasks. These learnable prompt vectors are initialized randomly or based on pre-trained node representations and then fine-tuned for different downstream tasks. But there are some drawbacks of these learnable soft prompts. The soft prompts are not related to the semantic instructions for specific tasks, and the effectiveness heavily depends on the quality and the diversity of the fine-tuning data in the downstream tasks. In this situation, they may bring the risk of poor generalization, particularly when fine-tuning data is biased or scarce, and most previous works freeze all parameters except these soft prompt vectors during downstream tasks. That could be suboptimal if a lot of new nodes appear during fine-tuning, especially when the pre-trained nodes in previous tasks cannot offer a direct reference to represent those new nodes in the downstream task. Given those drawbacks of learnable soft prompts, in this paper we will focus on using prompts based on plain text to provide graph models explicit guidance on different tasks. Such prompts guide the model through text instructions. These task-based instructions can accurately describe specific task requirements related to the graph data. For example, if three readers have read a book about the French Revolution, we can use one hyperedge to connect them and prompt the hyperedge with instructions through pre-training. Then in the downstream task, if we are prompting poetry if we are promoting poetry on our website from Renaissance period, the model can easily locate those people similar to previous readers of French Revolution as a target customer according to the connection between the French Revolution and the Renaissance. Here we formulate our problem in details. Assume we have a pre-training graph and a downstream graph. Both of them have task-specific instructions. We define the overlapping nodes in the two graphs as target nodes and other nodes as context nodes. Our goal is to learn the representations of these target nodes in the pre-training graph during the pre-training stage for better downstream performance. For example, these nodes can be the overlapping molecules of different proteins in protein classification or the overlapping users in cross-domain recommendation. In our framework, the graph will be firstly converted to a hypergraph where each hyperedge can connect multiple nodes simultaneously. The connection among nodes and hyperedges can be represented by an instance matrix. There are many ways to construct the hypergraphs for different graph tasks. For example, if the graph is a user graph, and we are going to recommend different items in pretraining and downstream stages, we will regard those overlapped users as a target nodes, while items as a context nodes. Then, for each of pretraining and downstream graphs, we will have a target hypergraph where users who interacted with one common item are connected by one item hyperedge. Similarly, we'll have a context hypergraph where items interacted by one same user are connected by one user hyperedge. To provide explicit guidance for hypergraph learning, the instruction-based prompt embeddings are constructed based on available task-related information. Each instruction in our work is expected to help capture the relationship between the nodes connected by one hyperedge. So the instructions and the formulated hyperedges are designed in one-to-one correspondence. Instructions can be formulated from task description, node descriptions, or combination of both. For example, in a target graph, different users who interact with one item are connected by one item hyperedge. Then the book description or the item description here is used as a hyperedge information. We encode the instructions by pretraining the language model and apply a prompt layer to adaptively learn the transformation from the text embedding to prompt embeddings. These prompt embeddings we are going to participate in the information propagation during the following hypergraph convolution. To integrate the information from the instructions into the hypergraph convolution process, we devise a novel prompt hypergraph convolution, or we call a PHC layer. First, we will initialize hyperedge information based on its connected nodes. Then we fuse the hyperedge information with a corresponding prompt embedding, which are encoded from the text-based instructions. Finally, we will update the target node embedding by aggregating the fused embedding from all its connected hyperedges. From its matrix form here, we can see that this prompt hypergraph convolution layer is a more general version of the hypergraph convolution. It will degrade to existing hypergraph convolution if we set the prompting intensities gamma equal to 0. After we use this PHC layer to get all nodes embeddings, for link prediction problem, we will use inner product between nodes as a prediction score and pairwise BPL loss as an object function. Different from previous graph prompt training method, in the downstream task, we will freeze the parameters in the prompt layer and fine-tune all nodes embedding with new downstream instructions. This allows us for dynamic adaptation of node representations to the specific context of the downstream task. Besides, we use different initial learning rates of Adam optimizer for target nodes and context nodes, since a lower learning rate for updating target nodes can prevent the framework from forgetting the pretrained knowledge. We evaluate our pretraining framework on the data from two real-world datasets, the Goodreads and Amazon. Users in this dataset are used as the target nodes existing in both the pretraining and the downstream stages, and the different categories of items are used as context nodes. We compare our proposed framework, IHP information, the instruction-based hypergraph pretraining with both recommendation baselines and the graph pretraining frameworks baselines. Notice that the first pretraining baselines, the attribute masking, it will predict the masked attributes which are node categories during the pretraining, and it's not suitable. This first pretraining baselines is not suitable for the first Goodreads poetry dataset because all the pretraining nodes in this dataset are in the same category. For the fair comparison, we will use a hypergraph convolution as a graph encoder for all pretraining framework baselines. We can see that with explicit guidance of instructions in the pretraining and fine-tuning, our framework gets a large and stable improvement in our dataset. And to quantify the contribution of pretraining language models as a text encoder for instruction information in our framework, we compare the performance of our framework with and without pre-trained language model in this table. We found that using pre-trained language model to encode instructions leads to stable improvements in our dataset. Benefits of each pre-trained language model depends on the dataset, and in this paper we'll use mini LLM as a text encoder in our framework. The instructions in our framework contain both node with item and text descriptions. And as an ablation study, instead of concatenating the node description and text information as one instruction to encode for each hyperage, we investigated 3 other variants of our method. The first variant is we only encode node description or item description as text embeddings, and then concatenate them to a randomly initialized learnable task vector for each task before prompt transformation. The second variant is the node descriptions and task descriptions are encoded by the pre-trained language model separately and then concatenated for prompt transformation. The third variant is that we let the encoded task information skip both prompt transformation and hypergraph convolution and only concatenate it to the final node embedding for prediction. The poor performance of the first variant verifies that the limitation of learnable vectors compared to the text-based instructions. And the other 2 variants also have worse performance because separately encoding node description and the task information, this way will ignore the semantic connection between them. We also do the ablation study of different fine-tuning settings. First, we can fine-tune or freeze the pre-trained target node embeddings in downstream texts. Freezing target node embedding saves the computational resource, but also reduces flexibility and limited adaptability to downstream data for the pre-training framework. This issue becomes more serious with a growing discrepancy between the pre-training and downstream data. As the figure shows, while the difference is not obvious in some smaller Goodreads dataset, the variant with frozen target node embedding can hardly adapt to the downstream data in the larger Amazon dataset, since all the items in Goodreads are only books, but Amazon has items in much more diverse categories. On the contrary, as this figure shows, updating the pre-trained prompt layer doesn't improve the downstream performance a lot compared with updating or say the fine-tuning the randomly initialized parameters. Since the task-related information is inherently encapsulated in text-based instructions, we believe that it is unnecessary to fine-tune the transformation during downstream text for learning the task-related information. In addition to these application studies, in our paper we also investigated the performance of our framework on node classification task and the performance of inductive representation learning for the unseen nodes in downstream graph. We will skip them here due to the limit of time. In conclusion, we designed a novel framework in IHP instruction-based hypergraph pretraining. To the best of our knowledge, this is the first pretraining framework to leverage instructions to capture high-order relations for graph tasks. To prompt the text-based instructions into hyperages, we propose a novel PHC layer allowing the instruction information to participate in information propagation during the hypergraph convolution. And we conduct extensive experiments on real-world dataset, and the stable improvements observed in the performance justifies its effectiveness on the hypergraph pretraining. Yeah, and I think that's all. Any questions?